Hello, welcome to the course on pericyclic reactions and organic photochemistry. We are now in module number 12. In this module, we will consider a very important reaction known as 1,3-dipolar cycloaddition reaction. 1,3-dipolar cycloaddition reactions are extremely important because they are used in the formation or synthesis of heterocyclic derivatives. As the name suggests, the 1,3-dipolar systems are essentially polar systems with the charged zwitterionic system in the carbon number 1 or in the atom number 1 and 3, for example, and they do undergo cycloaddition reaction to produce 5-membered rings. Now the generic examples of 1,3-dipole comes in two forms. It could be either in the form of allyl anion type, as you can see here with the bent structure, or propargyl allynyl type with the linear structure like this. Now this is what is known as the 1,3-dipole. This is 1,3-dipole because one can always write a canonical structure with the charges on the atom 1 and 3. In this particular case, the charges are written in atom number 1 and 2, for example. The 1,3-dipoles are 4-electron system. We will see it in a minute. They undergo a 4+2 cycloaddition reaction in terms of the number of electron count. They are thermal reaction. The 4-pi component is the 1,3-dipole component, and the 1,3-dipolophile can be either a alkene or an acetylene, as the case may be. So overall, these are reactions involving 6-pi electron system. So they are governed by the Woodward-Hoffmann rule as 4-pi suprafacial and 2-pi suprafacial cycloaddition reaction. They involve an aromatic transition state of 6-electron aromatic transition state, something like a cyclopentadienyl anion kind of an aromatic transition state you can imagine. The 4-pi component is referred to as the 1,3-dipole, which are these structures that are seen here. The zwitterionic structures, resonance structures are shown in this particular case. The 2-electron components is known as the dienophile, a dipolarophile. Similar to a dienophile, you have a dipolarophile, which is the acetylene component or the alkene component. They are used in the synthesis of 5-membered heterocyclic ring. As you can see here, the 5-membered ring is what is formed. It could be a heterocyclic ring if the atoms A, B, C are heteroatoms in nature, for example. There are several examples of 1,3-dipoles known in the allyl anion allyl type system. The classification is shown here. These are essentially allyl anion type, or the allyl type of system is what is shown here. Typical examples are azomethane halide, azomethane imine, nitrone, azime, azoxy, nitro, ozone, nitroso oxide, nitroso imine, carbonyl oxide, carbonyl imine, and carbonyl ylide. These are the examples which will correspond to the allyl anion allyl type of 1,3-dipole. You can see here in all these cases at least one heteroatom is being present in the 1,3-dipole, and that is what is responsible for the formation of the heterocyclic ring during the course of the cycloaddition reaction. For the sake of this particular module, we will consider azomethane halide and nitrone as examples of 1,3-dipoles undergoing the cycloaddition reaction in the subsequent transparencies. Now, classification of 1,3-dipole containing carbon, oxygen and nitrogen according to the Hughes-Jean rule in the propargyl allynyl type are as follows. You can have nitrile ylides, nitrile imines, nitrile oxides, diazoalkane, which are commonly known as diazomethanes, for example. The azides, which are very popular dipoles, for example, 1,3-dipoles, for example, leading to the formation of triazoles, we will see in a minute. Nitrous oxide, another example of a 1,3-dipole. In the module, we will see nitrile oxide and diazoalkane and azide as examples of 1,3-dipoles that are undergoing the 4-pi 2-pi cycloaddition reaction to form the 5-membered heterocyclic ring system in this case. From the frontier molecular orbital methodology, one can analyze the cycloaddition reaction involving a suprafacial kind of an approach. In other words, a parallel approach of the 1,3-dipolophile and the dipole 1,3-dipole. In this particular case, the top portion is the 1,3-dipole and the bottom portion is the 1,3-dipolophile. You can either consider the HOMO of the dipole and the LUMO of the dipolophile, or alternatively one can consider the LUMO of the dipole and HOMO of the dipolophile, as the case may be. In the case of HOMO of the dipole will have one nodal point, which is the central atom of this dipole, for example, whereas the LUMO of the dipolarifier is very similar to the LUMO of ethylene, for example. So if you are considering ethylene or acetylene, there will be one nodal point present here. So you can see here this overlap is a bonding type overlap. This overlap is also a bonding type overlap. So under the thermal conditions, this reaction is allowed under the superficial overlap kind of a mode of approach. Alternatively, if you consider the LUMO of the dipole, which is this particular fragment LUMO of the dipole, for example, the LUMO of the dipole will have two nodal points, one nodal point on this particular bond, the other nodal point in the other bond, for example, and the LUMO of the HOMO of the dipolarifier, which is this particular one. HOMO of the dipolarifier will have no nodes at all. So this doesn't have any nodes. So the overlap is essentially in this particular case a bonding type of an overlap here and a bonding type of an overlap real, which is thermally allowed process, and this is a superficial overlap of the dipolarifier and the dipole, as the case may be. I keep saying diene and dienophile because we have just finished the Diels-Alder reaction. The same terminology cannot be used here, unfortunately. Now the 1,3 dipolar cycloaddition reaction examples are shown here. Azomethane halide is the structure that is shown here. This is a 1,3 dipole. It undergoes cycloaddition reaction with an alkene to form the pyrrolidine derivative, or it can form a pyrroline derivative if it is undergoing a cycloaddition reaction with an alkyne. Similarly, nitrone can also undergo a cycloaddition reaction with an alkene to produce isoxazolidine or with an alkyne to produce isoxazolene. So these are the heterocyclic systems that can be generated by the cycloaddition reaction of azomethane halide and nitrone. Let us see how azomethane halides are generated. Before we go into that, in the case of the propargyl allynyl type of system, you have a nitrile oxide, diazomethane and azide as the examples. The reaction of the nitrile oxide with an alkene produces an isoxazolene, whereas with an alkyne it produces an isoxazole. Directly the aromatic heterocycle itself is formed in this particular reaction. With the diazoalkane, this is a very common reaction. Diazoalkane produce pyrazolene or pyrazole depending upon, this is a 3H pyrazole is what is produced in this particular case. And depending upon whether it is alkene or alkyne, one can produce these two types of heterocyclic derivatives. With azides undergo cycloaddition reaction with alkene to produce triazolene, or with alkynes to produce triazole, which is an aromatic heterocyclic compound, this particular case. Now let us look at the method of generation of nitrone first. Nitrones are generated by condensation of an aldehyde, in this particular case of formaldehyde, with a secondary hydroxylamine. So this is an alkyl substituted hydroxylamine. So the condensation essentially with the loss of water produces nitrone as the derivative. Alternatively, from a tertiary hydroxylamine, by oxidation using mercuric oxide, one can also produce the nitrone. So nitrones, there are two methods of producing the nitrone which are illustrated in this particular example. Once the nitrone is produced, it can undergo a cycloaddition reaction with a variety of both electron rich as well as electron deficient dipolarifier. This is an electron rich dipolarifier because of the oxygen that can donate a lone pair of electron onto the double bond. This is essentially an enol ether kind of a system, whereas all the other ones are electron deficient dipolarifiers. You can see here in the case of the electron rich and electron deficient dipolarifier, the reactions are highly regioselective in nature, in the sense that the regioisomer that is formed is this particular isomer that is formed by the reaction of the nitrone with the dipolarophiles. Whereas in the case of the nitroalkane, the regioselectivity is different. This is opposite isomer that is formed in the terms of the regioselectivity of this particular reaction. Quite often, diastereomeric mixture can be formed or regioisomeric mixture can be formed in the case of the 1,3 dipolar cycloaddition reaction. It's not always the reaction is highly regioselective in nature. It is possible that one can produce a mixture of regioisomers also in the case of 1,3 dipolar cycloaddition reaction. Here a mixture of cis and trans isomer is formed with respect to the relative stereochemistry of these two substituents that is present in this isoxazolene ring system that is formed during the course of the reaction. This particular nitrone undergoes cycloaddition reaction with the electron deficient dipolarified in preference to an electron rich dipolarified. There are two double bonds here. One is electron deficient because of the carboxylic acid ester groups that are substituted. This is relatively speaking electron rich. Dipolarophiles are electron deficient and dipoles are electron rich in nature. So that combination, electronic character combination, perfectly suited for this type of a reaction. You can see here this cycloadduct is what is formed exclusively during the course of the reaction. Now the nitrone cycloaddition reaction produces as an isoxazolene, and the isoxazolene can be made to undergo reductive cleavage of the carbon oxygen nitrogen bond to produce beta amino alcohol of this type. So other than forming heterocyclic ring, they can also be used to form stereoselectively the beta amino alcohol derivatives of this kind in the organic synthesis. Here is an example where a furanose derivative is formed by the initial addition of the hydroxy onto the oxime to produce this nitrone, which is formed by condensation of the initially formed hydroxylamine with the acetaldehyde, for example, resulting in the formation of this particular nitrone that undergoes cycloaddition reaction with alpha methyl acrylate to produce regioselectively this particular isomer of the cycloadduct. This cycloadduct is actually a aminol, which is this particular iminol is what is undergoing the hydrolysis to produce the isoxazolene ring in a 90% enantiomer selective manner, because the starting material is chiral in nature. This is a sugar derivative, so whatever the chiral center that is produced is enantiomer selectively produced. So this is an example of a first generation asymmetric transformation where you start with an enantiomerically pure starting material producing the enantiomerically pure product after the cycloaddition reaction is over. In this case, the asymmetric synthesis of isoxazolidine via Lewis acid catalysis was illustrated. The nitrone derivative undergoes cycloaddition reaction with this particular olefin, and 10 mole % of this magnesium magnesium complex is used as a chiral Lewis acid, for example. The magnesium triplet, which is coordinated to this bis-isoxazolene ring system, which is a chiral ligand, for example, produces a chiral Lewis acid. The chiral Lewis acid in turn coordinates or chelates with these two oxygen, producing a chiral derivative of the dipolarified, and that undergoes the cycloaddition reaction to endoselectively to give this particular product, for example, in an enantiomer selective manner. The exo-endo ratio is endoselective. It is 97% endo, and that 97% endo is formed in about 85% of enantiomeric excess. So overall, this is a chiral Lewis acid catalyzed 1,3-dipolar cycloaddition reaction of a nitrone to form asymmetric synthesis of isoxazolidine as the final product in this particular case. Here, the azomethane halide is generated by the decomposition of an aziridine. This is an azomethane halide that is generated by the decomposition of the aziridine. When the aziridine is heated to about 175 degrees, that produces this 1,3-dipole as an intermediate, which is trapped by a dipolarified, which is in this particular case tertiary butyl acrylate, for example, resulting in the formation of a regioselective formation of this particular cycloadduct in this case. Generally, azomethane halides can be generated from the decomposition of aziridine. Alternatively, they can also be generated by the decomposition of oxazolene. Oxazolines undergo decomposition to produce ring opening reaction to produce azomethane halide derivative that can be trapped either with an alkyne or an alkene, as the case may be, to produce the corresponding heterocyclic system in this case. This dihydroheterocyclic system can be aromatized by oxidation with the DDQ to form the pyrrole derivative, which is this particular derivative that is shown here. The mechanism of formation of the azomethane halide from oxazolene is given here. It is a simple thermal decomposition involving the lone pair of electron and the nitrogen, resulting in the formation of the cleavage of the carbon-oxygen bond, resulting in the formation of the 1,3-dipole, which is shown in this mechanism. Here is an example which is already seen in the case of the electrocyclic ring opening reaction. This also constitutes as an example of a 1,3-dipolar cycloaddition reaction. That is why this is brought in back here. This is an aziridine which undergoes thermal electrocyclic ring opening reaction. This is a 4-electron system undergoing conrotatory thermal electrocyclic ring opening reaction to produce this particular isomer of the azomethane halide. The azomethane halide thus produced is undergoing a cycloaddition reaction with the dimethylacetylene dicarboxylic acid, resulting in the formation of this particular adduct. Since the stereochemistry of the 1,3 polar derivative is this particular stereochemistry, the two ester functional groups are trans with respect to each other. When the other diastereoisomer is produced by the thermal decomposition of the diastereoisomer of the aziridine, then the diester that is produced in this particular case is cis diester, because the two carboxylic acid functional groups here are outside of the pi framework. In other words, the stereochemistry in these two carbon matters as far as the stereochemistry of the two carbon centers that are produced in this particular derivative of the cycloadduct. Under photochemical condition, of course, this will undergo a disrotatory ring opening, so producing exactly the opposite stereochemistry. Initially, you saw in the case of thermal rearrangement, thermal condition, the cis isomer produces this particular compound, whereas the cis isomer under photochemical produces opposite diastereoisomer that is trapped by dimethylacetylene dicarboxylic acid to give the cis ester in this particular case. The trans isomer produces the opposite diastereoisomer of the azomethane halide, and that is trapped by dimethylacetylene dicarboxylic acid to give the corresponding cycloadduct with this particular stereochemistry that is shown here. Here is another example of an intramolecular cycloaddition of the azomethane halide. This aziridine is decomposed and there is an inbuilt double bond which is the dipolarophile in this particular case. So the dipole that is formed is trapped by the dipolarophile, which is this dipolarophile, resulting in the formation of this adduct in this case. Same example, except the dipolarophile now is a alkyne. It undergoes the cycloaddition reaction by the azomethane halide that is produced by the decomposition of the aziridine ring to form the corresponding pyrrole derivative in this particular case and pyrroline derivative in this case. Some more examples of intramolecular versions of the trapping of the azomethane halide by an alkyne. Here is a pyridine substituted vinyl derivative that undergoes the 3+2 cycloaddition reaction to produce this corresponding heterocyclic derivative in a regioselective manner, because there is only one regioisomer that is possible for this tethered group that is being attached to the azomethane halide in this particular case. Now this slide tells you something about the asymmetric synthesis of pyrrolidine derivatives. You are starting with a asymmetric optically pure isomer of a derivative, which is this particular derivative, which is a secondary amine that is condensed with the aldehyde to produce the azomethane halide. The azomethane halide thus produced is trapped by dimethyl ester of the maleic acid, for example, resulting in the formation of this particular derivative. This derivative now undergoes hydrogenolysis of this benzyl carbon nitrogen bond and the carbon oxygen bond to produce the corresponding pyrrolidine derivative, where 3 stereocenters are produced. The 4th stereocenter is not very well defined in this particular case. However, the compound that is formed is produced in 99% yield with 99% of enantiomeric excess of only one of the diastereoisomers of this particular molecule that is produced here. Another example of an asymmetric synthesis using chiral auxiliary. Here in this particular example, this decomposition of this aziridine derivative produces the azomethane halide, which is this particular molecule. And here is a sultam which is used. This is the camphor derived sultam, and the dipolarophile is attached to a camphor derived sultam as a chiral auxiliary. The cycloaddition reaction between the dipole that is produced with the dipolarophile, which is a chiral dipolarophile, results in the formation of an enantiomerically excess, in other words constituting an asymmetric synthesis using a chiral auxiliary of this particular pyrrolidine derivative that is given here. So what we have seen in this particular module is examples of 1,3 dipoles from the point of view of the allyl anion type as well as the propargyl allynyl type, and the cycloaddition reactions of the allyl anion type of systems, namely the azomethane halide and the nitrone derivatives, to form the corresponding heterocyclic derivative. Thank you very much for your kind attention.